I think that's what we have in terms of practicalities. So welcome to the April 27 installation of the Beyond Satisfiability seminar series. So the goal of this seminar series is to go beyond SAT, go beyond NP. And for some people, NP is not enough. They want to solve all of P space. And you want to do that, to do quantified Boolean formula solving or QBF solving. And today, Florian Lonsing from Stanford and Martina Seidl from Johannes Kepler University Linz will tell us about the secrets of QBF solving. So this will be, if I understood correctly, a kind of tutorialish talk in two parts. So Florian will guide us before the break, and then after roughly an hour, maybe we have a break, and then Martina continues. Something like that. Yes? So Florian, without further ado, please.
Thank you, Jakob, for the introduction. As Jakob mentioned, we are going to give you an overview of QBF solving today. And by doing that, we aim to address one of the main questions of this workshop. That is, how can we generalize efficient satisfiability methods to problem domains that are beyond NP? And in particular, we are targeting the P-space domain here. So QBF solving is P-space complete. It's the canonical problem in that class. And being that, it is a natural candidate for effectively encoding problems from that class or from any class in the polynomial hierarchy. So we're going to give you an overview over the main two of the main solving paradigms for QBF. But before that, let's have a look at some context. In general, we are interested in applying logic-based methods to solve hard combinatorial problems, for instance. So on this chart, you can see an abstract workflow that we typically apply to solve such problems. So given some instance of a problem, we would first encode that problem in some logic. This could be propositional logic, QBF, or first order logic, for instance. And then this is an optional step. We apply pre-processing in order to remove redundancy, for instance, or to make sure that the encoding has certain properties we want it to have. In the next step, we apply solving. So we apply a theorem prover or a SAT solver, QBF solver to solve our encoding. And ideally, the solver provides us either with a proof that the instance is unsatisfiable or with a model showing us that it is satisfiable. So the model is typically an assignment to the set of variables. And given that model, we can then map the model back to a solution to the original problem, which gives us then a solution to the original problem that we were interested in solving. So that's a very abstract flow which applies to logics in general. In particular, it has been shown in the past 20 years that this workflow is very effective in the context of propositional logic. So there we have methods to efficiently encode problems to remove redundancy. This is also done in a more dynamic way in processing, for instance, in CDCL solvers. This has been shown to be very effective in practice. Also, there has been a tremendous improvement in heuristics combined with low-level optimizations, such as clever memory layouts and related techniques. It is also important to have efficient and reliable proof checking in order to increase reliability of the results that we obtain from that workflow. And just to give you a very prominent example, there was a famous combinatorial problem, the Boolean Pythagorean triples problem, which was solved using SAT-based techniques. We take this example and in general, the success story of SAT as a motivation to actually obtain a similar success story in the field of QBF solving. So that's what we are aiming at. We want to establish QBF solving as a general technique to solve P-space problems and beyond. So in this talk, we focus on quantified Boolean formulas. This is an extension of propositional logic. where we have existential and universal quantification over the propositional variables. The presence of quantification renders the satisfiability problem p-space complete, which is in contrast to the NP completeness of propositional satisfiability. So under the typical assumption that NP does not equal p-space, as a consequence, we have that QBF checking is harder. On the other hand, we can expect that the problem encodings in QBF are exponentially more succinct than propositional encodings. So in this talk, we will be focusing on QBFs in Prenex conjunctive normal form, as shown on the slide here. These formulas consist of a quantifier prefix and a propositional CNF. In terms of semantics, QBF can be characterized by assignment trees. This is in contrast to propositional logic. In propositional logic, a model is just a single assignment to the variables which satisfies the formulas. Whereas in QBF, we have to actually find a satisfying assignment tree. So let's have a look at the example shown here on the slide. The formula shown here is encodes the equivalence of x and y under the prefix for all x exists y. So this is a satisfiable or true formula because whenever we set x to false, we can also set the existential variable y to false and thereby satisfy the propositional CNF. And similarly for the variable assignments where we set the variables to true. What we also can see here is a dependency of the existential variable y on the universal variable x. So whenever the universal variable x is set to false, the existential variable has to be set with respect to the current valuation of the universal variable. This is also often presented as a two-player game, actually, where the universal player controls the universal variables and aims to falsify the CNF, whereas the existential player, who controls the existential variables, tries to satisfy the CNF. And the existential player, in this example, has to respond with a variable assignment to whatever assignment the universal player has made before. There is a similar concept of assignment trees for unsatisfiable or false formulas, which represent counter models of false QBFs. So this is exactly the same CNF, but here we have flipped the ordering of the variables. Now the prefix is there exists a y such that for all x, the CNF is true. And this is no longer the case because if we fix the value of the existential variable, then the universal player has always the opportunity to falsify the CNF. And this assignment tree actually witnesses that for whatever value of the existential player, there is a way to falsify the CNF. Another way that's often used to represent QBF semantics, which is closely related to assignment trees and the two-player game semantics, is the semantics in terms of Skolem functions. A Skolem function is a function related to the existential variables of the formula, which tells us essentially how the existential player has to respond when given a current move of the universal player. So in this example, f sub y is this Skolem function that represents the assignments of the existential player when given x, which is the assignment of the current assignments of the universal player. So this is an equivalent way of thinking about the QBF semantics. Now for false QBFs, we have a related concept called Abron functions, which is dual. Abron functions represent, in this case, f sub x is the Abron function for the universal player, and it tells us how to respond to a given move of the existential player, y in this case. One important syntactic concept that we are interested in is the number of quantifier alternations in a Prenix CNF. A given Prenix CNF has a sequence of quantifier blocks QI, BI, where QI is a quantifier and BI is a set of propositional variables. So in this example shown here, the first block consists of two variables x1 and x2, second block of u1, u2, and so forth. This sequence of blocks is linearly ordered. It introduces a total ordering on the variables, where blocks which come first are considered to be smaller than later blocks in the sequence. We assume that adjacent blocks have a different quantifier type, so QI is different from QI plus 1. And under this assumption, a QBF with a PCNF with n quantifier blocks has n-1 quantifier alternations. And this is actually useful for theoretical considerations because the satisfiability problem, the complexity of the problem is closely related to the polynomial hierarchy, which is a theoretical framework to describe the complexity of problems beyond the class NP. An important theoretical result in that framework shows that given a PCNF with k alternations, the respective satisfiability problem is located at level k plus 1 in the polynomial hierarchy, where the type of the first quantifier actually tells us whether it's sigma k plus 1 complete, or for the universal quantifier, whether it's p k plus 1 complete. Given this characterization, we can actually have a look at the polynomial hierarchy and identify a set of useful and interesting problems in practice. So at the first level, we have the classes NP and co-NP, which correspond to propositional logic satisfiability and validity checking. And if we go to higher levels, we find interesting problems like MUS membership testing of clauses. So this is minimal unsatisfiable subsets of CNFs. There are a couple of problems related to planning, answer set programming, abstract argumentation, and so forth. So this is just to give you an idea of the variety of problems that we can work on here. Finally, the further up we move, we reach the class of P-space eventually. This is a class of problems where the number of quantifier alternations depends on the problem instance. So that's a parameter here. And one prominent example in this class is model checking of linear time temporal logics, for instance. There are also a couple of automata-related problems like language inclusion checking for non-deterministic finite automata, and many two-player games that are P-space complete. So there's lots of applications that are amenable to QBF-related techniques. Of course, we mentioned that already. The hardness of QBF comes at a cost. So P-space is deemed harder than NP, but also offers opportunities in terms of having more compact encodings compared to propositional logic. And there is even, if we move higher up in the complexity hierarchy, there is an extension of a generalization of quantified Boolean formulas, which is called dependency QBFs, where the satisfiability problem is nx time complete. So it's even harder than P-space, presumably, but this would offer additional exponential savings in terms of encoding sizes. So this is what we get in terms of opportunities. Now we move closer to the topic of our talk today, QBF solving. When we compare this to the history of SAT solving, then we find that QBF solving is actually a young field of research compared to SAT. SAT started in the 1960s with DPLL, whereas QBF started essentially in the late 90s. We have a variant of DPLL for QBF, which was published in 1998. So it's a bit more than 20 years ago. And this was later extended to closed learning. This is essentially a variant of CDCL for QBF. And at the same time, expansion-based approaches were published. And these are the two topics actually where we are going to focus on in the talk today. In the past 20 years, there has been an increased interest in QBF solving. So not only on the practical side, but in particular in terms of proof systems. So we have a much better understanding now how to characterize the approaches that were implemented in early solvers. And we also know new avenues how to improve existing approaches in terms of making use of knowledge in proof complexity. For instance, it is now well known that close learning, CDCL and expansion are orthogonal. So each of these approaches have their own strength and weaknesses. One other important line of research is QBF solving based on counterexample guided abstraction refinement. This is the well-known SIGA approach that came up in the domain of model checking. Let me make a quick announcement here. Martina and I are involved in the organization of the QBF workshop, which is affiliated at SAT this year. So if you are interested in QBF, or even if you are working on a problem that's related to QBF, please consider submitting a paper. So contact any of the organizers. We would be very much welcome to host your talk at our workshop. We also have a recurring QBF solver competition, QBF Eval, which takes a break this year, but will be back next year. And this solver evaluation, as was seen with the SAT competition, for instance, has been an important driving force in the development of QBF solvers. So to give you a brief outline of what we are going to present next, we are going to focus on the solving stage in this abstract workflow. And we are going to give you an overview of two of the main paradigms. First, search-based QBF solving, which is a variant of CDCL essentially. And then in the second part, we will cover an orthogonal approach, which is based on expansion. And we are also going to consider some of the theoretical properties and proof systems that underlie these systems. So first of all, what we are going to do is we go back to the late 90s now. So we are in the year 1998, where this first search-based approach, the DPLL algorithm for QBF, was published. This is on a high level a rather simple algorithm, but it came already back then. It came with quite sophisticated improvements, which we will analyze in the following. So the pseudocode here shows a recursive implementation of DPLL for QBF. Here we are given as input a PCNF C and an assignment A. And as a first step, what we do, and this is related to SAT solving, for instance, to the implementation of CDCL, we first simplify the formula under the given assignment A, which gives us a formula C prime. Then in the second step, we check whether we hit one of the base cases where this simplified formula is actually true or false, meaning a syntactic constant true or false. And if this is the case, we terminate. And otherwise, we extend the current assignment by decision making. So we pick a variable from the prefix. In that case, we assign the first variable in that prefix and branch, and then branch recursively. And depending on the quantifier type, we have to consider different semantics here. So if the variable is existentially quantified, we have to find that either of the two branches yields a satisfying result. And for the universal variable, we have to find that exactly both branches yield a satisfiable result. So that's a quite straightforward implementation of QBF semantics, actually. Yeah, I mentioned that this is still chronological backtracking. And one important improvement that was implemented already in the first version was an improvement of how we generate assignments. So here, what we do is only decision making, which is a rather weak weak way to generate assignments. And in the following, we're going to take a look on how we can improve in terms of making assignments. One way to do this is to lift Boolean constraint propagation, which is known from set solving to QBF. This is what we call QBCP. And this is, it's related to BCP as it is implemented in set solvers, but it's more general because it now has to deal with the universal quantifiers in the formula. And one particular way to deal with these variables is by a technique called universal reduction, UR. This is a technique which was published in a seminal paper in 1995 by Kleine-Bühning, Kapinski, and Vögel, which we will see also later when it comes to resolution-based techniques for QBF. So universal reduction takes a clause and deletes all the literals L, all the universal literals L, for which the existential literals L prime in that clause are smaller than the universal literal with respect to the prefix ordering. So essentially, we inspect the clause and we delete all the universal literals that are trailing in the clause. So consider, for instance, this example here. Universal literals are shown in red for simplicity. If we apply universal reduction to the first clause, then we can see that we cannot delete any literal here because the universal literal y1 is smaller than the existential literal x1. So y1 is not trailing, so we cannot delete it here. On the other hand, for the second clause, we find that y2 is trailing, and therefore it can be deleted. So x1 is smaller than y2, and there is no other existential literal in that clause which would prevent the reduction of y2. So we actually can shorten that clause here. And in the extreme case, for a clause which contains only universal literals, like the last one here, we can reduce that clause immediately to the empty clause, showing that the formula is unsatisfiable. So as you can see, this is a powerful technique which, in combination with unit propagation, can bring us closer to identifying an unsatisfiable branch in the search tree. And in terms of theory, it was shown that universal reduction is a technique which can be used to construct QBF proof systems. So essentially, we can take any propositional proof system, add the universal reduction rule, and the result will be a complete QBF proof system. So this is just as a note that this is not just an implementation technique that we are using, but it's also a technique that is used for theoretical considerations. Universal reduction is part of QBCP, in addition to unit propagation and also pure literal detection, which we are going to consider next. Unit literal detection is very well known from set solving. And in the context of QBF, it works in essentially the same way. So a given clause C is unit, if and only if it consists of a single literal L, which is existentially quantified. Given that, we can then set the variable of L such that the clause is satisfied. So it's exactly the same as in set solving. Yeah, this is a simple example here, and the given formula contains the unit clause x2, and we just set x2 to true by following the unit literal assignment. QBCP has a third rule, which is pure literal detection. This was, I guess, also part of the early DPLL algorithm for set, but it's no longer used explicitly in modern set solvers because it's deemed to be too costly in practice. However, for QBF, it was found that it is very effective also in pruning parts of the search space. And in particular, if we consider unsatisfiable formulas and formulas which contain lots of universal variables. So this rule works as follows. we say that the literal L is pure in a formula if there are clauses which contain L positively, but no clauses which contain L in the other polarity. And if this is the case, then we can assign the variable of that pure literal, where the assignment depends on the quantified type. So if the literal that is pure is existential, then we assign it in such a way that we satisfy all the clauses where it appears. And if it's universally quantified, we set it in such a way that we don't satisfy the clauses, so that we actually shorten all the clauses where that variable occurs. This is illustrated in the example here. Here we have a formula with a universal variable y, which appears only negatively in the formula. So what we can do here by the universal pure literal rule is we can set y to true, and this will shorten all the clauses where the literal not y appears. As you can see, this is also a technique in particular for universal variables, which brings us closer to identifying unsatisfiable parts of the search space due to the shortening of clauses. Now, to put everything together, QBCP, Boolean constraint propagation for QBF, applies these three techniques until saturation. So we run universal reduction until there is no change in the formula. We run unit literal detection and pure literal detection until there is no change anymore. And we collect all the assignments through these runs. Whenever we find that the formula reduces to true or false under the currently identified assignments, then we would immediately terminate. So that's, as you can see, an extension of BCP for set solving. In set solving, we typically only apply in the basic form unit literal detection, whereas in QBCP for QBF, we also have universal reduction and the pure literal rule, which can or typically do influence each other. So we will see this in an example later on, that universal reduction due to the shortening of clauses can enable additional unit propagations. And for instance, this is also true for pure literal detection. So there is an influence between these rules. So let's have a look at an example here. This is a formula where initially no simplifications by QBCP are possible. So what we do is, in order to solve this formula, we first make a decision on variable, on the first variable in the prefix, which is the universal y5 here. We set this to true and simplify. And this will shorten the first clause and make it a unit, so we can propagate x4. This will result in additional simplifications. In particular, it will shorten the second clause in the formula. Now, notice that y2 is trailing in this clause, so we can apply a universal reduction. And this produces a new unit clause x1. But let's say we first propagate or apply pure literal detection. Notice that the literal not y2 appears only negatively in the formula, but not positively. So we can set the variable y2 to true. In the next step, we propagate the unit clause x1 that we have identified. And then we have a formula derived which contains two complementary unit clauses. So this immediately shows that the formula is unsatisfiable, because the decision variable that we have assigned initially was a universal variable, and we have shown that this single branch already leads to an unsatisfiable subcase. So we are actually done, and we have shown that this formula is unsatisfiable with only making a single decision. So this example shows that QBCP actually tremendously increases the reasoning power of initial and basic DPLL implementations. So in order to integrate DPLL, to combine QBCP with DPLL, we actually apply it before decision making. So this is a chart which illustrates the general workflow.
Florian?
Given the formula and the assignment A, we first apply QBCP until saturation. This gives us a simplified formula psi prime. Then we detect whether we have hit one of the base cases. If this is not the case, then we assign a variable from the beginning of the prefix in decision making and start over with QBCP. Otherwise, if we have hit one of the base cases, then we analyze whether there are open subcases, open branches to be explored. If this is not the case, we terminate, and otherwise we backtrack. That is, we undo a subset of the current assignment and start over with QBCP. So this is the basic DPLL workflow. It was extended to from chronological backtracking to non-chronological backtracking, and in particular, it was equipped with clause learning. And this is now what we are going to look at next. And in particular, we are going to look at resolution proof systems for QBF, which can be used to do clause learning in a CDCL approach.
Florian, can you hear me?
Yes.
So just out of curiosity, the constraint propagation seems to be in some sense much more powerful than in the CDCL setting, and we know that in CDCL it's very important with these two watch literal schemes and other tricks. Are there like similar nifty implementation tricks that are very important for QBF solving, or like anything you can say about
yes,
that?
absolutely, yeah. We also have watched literal techniques for pure literal detection and for unit literal detection. Yeah.
Okay.
So that's absolutely crucial for performance in practice. Yeah, that's a good comment. Thanks for that. All right, so we now want to equip this workflow with clause learning, and in order to do that, we need to have a way to produce clauses, and like in a CDCL-based set solver, we do this by a resolution proof system. And for QBF, the first resolution proof system was the Q-resolution calculus, published in 1995 in that seminal paper by Kleine-Bühning, Karpinski, and Vögel. It's in some sense a lifting of propositional resolution to the QBF setting. So let's have a look at the rules in that system. We have an axiom rule, which is called init here, which just tells us that we can use any clause that appears in the original formula, provided that this clause is non-tautological. So there is always, as you can see in each of these rules, there is a side condition which tells us that we cannot use any tautological clauses. And the reason for that is that we will see that a bit later, that tautological clauses can result in unsoundness on the one hand, and on the other hand, they can provide additional power. So care has to be taken in terms of tautological clauses. The second rule is the universal reduction rule, red here. This is exactly the same as it is used in QBCP. It's just formulated a bit different. So we can give them a clause C where some literal L appears. Where L is universal, we can drop L from that clause, provided that it is a trailing literal in that clause. So it's exactly the same as in QBCP. Now for resolution, as shown on the bottom here, we have the requirements that the pivot variable P, which appears positively in one clause and negatively in the other, is existentially quantified. That's important. And we are not allowed to produce a tautological resolvent in the end by applying this rule. So let's have a look at an example. This is a simple formula with two clauses. Initially, what we do is we apply universal reduction to delete the trailing universal literals y2 from the first and not y2 from the second clause. This produces shortened clauses where we have a pivot variable x1 and not x1, which we can then use to make a resolution step. And finally, by universal reduction, we get the empty clause. It was shown in the original paper from 1995 that Q resolution is refutationally complete for PCNFs. That means a PCNF is unsatisfiable if and only if we can derive the empty clause by Q resolution. Now recall that we have two important restrictions. There is the restriction on the quantified type of the pivot, which must be existential, and we are not allowed to produce tautological resolvents. The completeness holds under these restrictions. However, as we shall see in the following, if we lift these restrictions, then we get an exponential increase in the power of the proof system. At the same time, this also increases, of course, the search space of the proof, of how to find the proof. Because now that we have, when we lift these restrictions, we have more opportunities for making inferences, and this makes it more difficult to find short proofs, even if they exist. One of these powerful proof systems that we get from lifting restrictions is called long distance resolution, or LD Q resolution. And this is a variant of Q resolution where we are allowed to produce tautological resolvents under certain side conditions. The axiom rule is not shown here. It's exactly the same as in Q resolution. For long distance Q resolution with universal reduction, here we have to make sure that we have to be aware of that we are now allowed to delete universal literals which appear complementary in the clause. These literals Y star are called merged literals, and this is just a shorthand for an occurrence of a universal literal Y and its complement not Y. So whenever we see a Y star, this means that the given clause is a tautology essentially. So universal reduction now allows us to delete these merged literals in the same way as the non-merged, the usual universal literals, under the same ordering restrictions. So whenever a universal literal, whether it's a merged one or not non-merged one, is trailing, we can delete it from the clause. And for the resolution rule, we now are allowed to produce tautologies. So for instance, assume that there's a universal literal L1 in one clause and L2 in the second clause, and these literals are over the same variable. Now, if L1 is the complement of L2, or if either one is merged, then the resolvent would contain a merged literal, meaning that it is tautological. And if this happens, we have to make sure that the pivot variable P is smaller than the variable which causes the tautology. So this is a bit involved. Let's have a look at an example. This is the same formula from before. We can, according to the long distance Q resolution rule, select x1, variable x1 as a pivot, produce a tautological clause, and note that here what happens is we merge the positive literal y2 and the negative literal not y2 to produce a star literal, the merged literal y2 star. And this is possible because y2 is trailing in these clauses, first of all, and also more importantly, the pivot is smaller, x1 is smaller than the merged literal y2 star that we produce in the resolution step. And given this clause, we can then apply a universal reduction and derive the empty clause. So this is a sound approach. It was shown in a paper from 2012 that this is sound in terms of this calculus. Interestingly, it was discovered already in 2002 in a paper by Sheng and Malik, who realized that it is sound to learn tautological clauses in CDCL although it wasn't formulated as a calculus back then. It's important to note that long-distance Q resolution is exponentially stronger than traditional Q resolution. This means that there are formula classes for which traditional Q resolution produces only exponential size proofs, whereas Q resolution, long-distance Q resolution produces polynomial size proofs. So this was one long-distance Q resolution is one powerful proof system we get when we lift one of the restrictions, that is the tautology restriction. The other restriction that we had in Q resolution was the pivot quantified type. We can also lift that restriction, so we just drop the requirement that the pivot has to be existential. That means that we can now resolve on existential and universal variables in a similar way. The rest of the rules don't change, actually. The resulting calculus is called QU resolution, and it's most similar to what we know from propositional resolution now. Interestingly, this also results in an exponentially more powerful system than traditional Q resolution. As a final step, we can actually lift both of these restrictions at the same time, and this results in a system called LQU plus resolution. So in that system, we can resolve on existential and universal pivots, and we can produce tautological resolvents. And this is actually currently the most powerful known resolution proof system. Here we have the hierarchy of the resolution-based system that we have just discussed. At the bottom, so if we go from the bottom to the top, systems become more powerful, exponentially more powerful. We have traditional Q resolution at the bottom, and a solid line indicates that the system on top is exponentially more powerful than the system at the bottom. And in this case, for long-distance Q resolution and QU resolution, it holds that these systems polynomially simulate Q resolution. That means any Q resolution proof is also a valid QU or long-distance Q resolution proof. It's interesting to note that long-distance Q resolution and QU resolution are what we call incomparable. That means that there are exponential separations between these systems. So there are formulas which have short proofs for QU resolution, but exponential proofs for long distance, and vice versa. So there's an exponential separation here. And for the most powerful system, LQU plus, this system simulates both of long distance Q resolution and QU resolution, and is exponentially stronger.
Florian?
Yes. Yeah.
Is there anything more you can say about these mysterious merged literals? I mean, what's confusing is if I just gave you an original clause that was Y or not Y, that's clearly tautological, and erasing both of these literals would clearly be unsound, right?
Yes.
But somehow magically,
yeah.
when they come from different clauses, suddenly it's okay to get rid of them. I mean, how?
Yeah, one way to think about this is in terms of the Braun functions. When you extract Braun functions from a long-distance Q resolution proof, then these merged literals give you, in some sense, an if-then-else chain, which tells the universal player how to respond to the moves of the existential player. But I agree that this is a bit mysterious. I completely agree.
Okay, thanks.
Yeah, in the following, I'd like to briefly mention, in the interest of time, some further extensions of these proof systems, these resolution proof systems, which result in potentially exponential benefits. Recall that we have this linear prefix in a Prenix CNF, which introduces a total ordering of the variables. This imposes quite severe restrictions in CDCL in terms of how we can assign variables, and it's also related to the universal reduction rule, as we have seen. There is a way to relax this total ordering, and this can be done by dependency schemes. A dependency scheme is a framework for expressing the independence of variables. Essentially, it's a binary relation D over the set of variables, such that if there is given two variables x and y, if x and y are unrelated in the relation, then we say that y is independent from x. And otherwise, if x and y are related, then we say that y depends on x, but that's a conservative statement here. So the assumption is that we can compute this dependency relation D in polynomial time, which of course is necessary here because there are formulas which for which this cannot be computed in polynomial time, because otherwise we would have a polynomial time algorithm for p-space. So this is in practice, for many formulas it can be computed, but that's not the general case. But the hope for practical applications is that we can compute it in polynomial time and then use it as a refinement of the total ordering. So essentially, in practice, this dependency relation D is a refinement of the total ordering, resulting in a partial ordering of the variables. We can use this dependency relation in practice to refine the universal reduction rule by just replacing the total ordering by the dependency relation. So in order to drop a universal literal L from a clause, we have to make sure that that universal literal L is unrelated to any existential literal L prime in that clause. And there's an interesting body of related work that came up where soundness criteria were proved for different dependency relations. And it was also shown that this more powerful universal reduction rule can be combined with different resolution proof systems. One important theoretical result was that applying this more powerful universal reduction rule actually gives you an exponentially more powerful Q resolution proof system. So this is already the case for the combination of traditional Q resolution with this dependency aware reduction rule. In another approach, this was actually brought to the extreme. This is called dependency learning. Here we would start tentatively with an empty dependency relation, then just apply QCDCL, and whenever it turns out that we have missed a dependency, we have made, for instance, an assignment which broke the dependency relation that's inherent in the formula, then this would be detected by the failure of producing a learned clause. And in that case, we would add the dependency x and y that was missed and start over again. So this is an interesting line of research which gives you additional exponential improvements for the known Q resolution calculi. Another approach that gives an exponential benefit is based on exploiting symmetries. So here we have a symmetry rule which we can add to any Q resolution calculus, and it tells us that from a given clause C we can derive the clause sigma C, where sigma is a symmetry, and the symmetry is a bijective mapping between the sets L and the literals of the formula, which has certain properties. In particular, we have to preserve the negation of the literals, the application of negations, and we have to make sure that the literal x and sigma x, the literal where we map that x to, appear in the same quantifier block. So it has to respect the total ordering of the quantifier prefix. Interestingly, this is when we add the symmetry rule to Q resolution, we get an exponentially stronger system. And it was even shown that if we do this dynamically, so if we recompute the symmetry mapping dynamically under the current assignment in, for instance, the assignment derived by QBCP, then this gives additional exponential gains. Also, this was this symmetry rule was generalized to homomorphisms. This means the mapping sigma is no longer required to be injective. And in that approach, also this quantifier block restriction was relaxed to some extent. And this again gives exponential benefits. So to show you the final picture, this is an abstract workflow of QCDCL. It's very similar to what we have seen for QDPLL. We have QBCP as an important stage. We detect whether we hit one of the base cases. If not, there's again decision making. But now clause learning comes in at the stage where we check whether we have open subcases. And this is very similar to clause learning in a propositional set solver. However, there are, due to the universal variables, there are some challenges that have to be overcome in terms of implementation. In particular, it turns out that in practice, only long distance Q resolution and traditional Q resolution was applied for clause learning. We have not yet found an efficient way to apply a QU resolution or this most powerful LQU plus resolution system that we have seen. And the reason for that is that, like in a CDCL set solver, the pivots in clause learning are chosen only from the existential variables by means of the variables that became unit during QBCP. And this naturally, for instance, prevents to select universal pivots, as would be necessary for QU resolution. Otherwise, we have similar concepts like implication graphs and asserting clauses in QCDCL. Also, what we haven't covered here is learning from satisfiable branches in the search tree. This is what we call cube learning. A cube is a conjunction of literals. And whenever we hit a satisfiable branch in the search tree, we can essentially learn that branch or a subset of it as a cube and add it to the formula. So in practice, a QCDCL solver maintains a set of original clauses that were given at the beginning, a set of learned clauses, and a set of learned cubes. Now, the drawback, of course, when you start with CNF is that this set of learned cubes grows exponentially in the worst case for a satisfiable QBF. And there are approaches, lots of approaches actually for non-CNF QBF solving, which can overcome this problem to some extent. All right, to wrap this part up, I'd like to show you this hierarchy of proof systems once again. In gray, we have the resolution proof systems that we have seen. In the second part, Martina will show you approaches for expansion-based solving, and these approaches are based on a proof system called for all expand plus resolution. As you can see here from this picture, this expansion-based approaches are incomparable. They are mutually separated, exponentially separated from the resolution proof systems. This is true for traditional Q resolution, as indicated by this edge here, but also this is true for the most powerful LQU plus resolution system. So what we expect from these expansion-based approaches is actually an orthogonal workflow, which in some cases could exponentially outperform Q resolution-based solving, but this also holds in the other direction. So there are formulas for which expansion is provably exponential, whereas Q resolution-based approaches are polynomial. yeah, with this, I'd like to conclude my part. And if we have time now, I would be happy to take questions, or also could take questions in the end, whatever is suitable.
We certainly do have time for questions. So what usually happens now is that we have a 10-ish minute break. But before we take the break, if there are any questions, please feel free to just unmute and speak. It's also okay to type the question in the chat, and I will try to read it out. And we can also collect questions in the chat and discuss them after the break.
There was a comment from Matte. Is there also a question related to this comment?
Yeah, so
please, not much. I think it was more like a statement that I realized that Florian meant it differently. So we don't actually have few little detection on what we would call on the fly. We only have it at what we would call top level. And I think what you meant is this that you have it at on the fly, so at every decision level. But we actually do have it at top level, and it's part of, well, it's implicitly part of what we call bounded variable elimination, and it's part of every sub solver that I know in the past 10 years approximately.
Yeah, thanks a lot. I certainly meant that in QBF we do this dynamically at every decision level. Yeah.
Yeah, all makes sense. Yeah, exactly. We don't have it at every decision level.
Okay, thanks.
There's a question in the chat from, let's see if I can expand to see the name, from Suhan. Is there any work on combining linear arithmetic with QBF solving, like in SMT solvers?
I think in theory, in the field of proof systems there is, but I'm not aware of any practical implementations, as far as I know.
Well, I can say Katalin worked with you, Florian, on the uninterpreted functions with QBF. Used your QBF solver actually.
Okay. Yeah.
Now you remember, right? Okay.
Yeah, but I'm not sure whether how far did we get with that?
Well, it's described in a thesis. There's one chapter, but it's like there's no paper, so that's the only thing out there.
All right.
Okay, any other questions before we take a break? Otherwise,
excuse me?
Yes, Massimo.
Okay. I was curious about you did. I don't know, maybe I missed it, but you didn't mention, or maybe you didn't go far mentioning about certificate of the proof. I mean, you have all these proof systems that you described, and I would expect this proof to. I mean, what's the strategy when about proof certificates here, especially because, of course, there's no difference between valid or contradictory and so on and so forth. So can you say something about it?
Yes, we know for these systems that are shown here that it is possible to extract Skolem and Erbrau functions from a given proof. These extraction algorithms are polynomial in the proof size, although the proofs themselves, of course, can be exponential in the formula size.
Yeah. Okay, thank you.
But in the QBF evaluation, like, would there be a requirement for proof logging, as in the SAT solving competition, or no?
Currently, we don't have that, and the reason is that we are still lacking a uniform proof format. So ideally, we would want to have something like what DRET is in this propositional world, but we don't have that at the moment. So it's possible to use, for instance, a generalization of DRET, which is called QRET, to produce certificates for satisfiable formulas. But this is still part of ongoing research to come up with a uniform format for proofs.
Okay, thank you. So then let's take a break and let's reconvene. Yeah, so 17 minutes to the hour, right? Something like that. Okay, so we are about to reconvene in a couple of minutes. If you have any questions, thoughts, comments after the first half of the seminar, now is a good time to use the chat or unmute and speak.
May I say something?
Which speaker? Yeah, Thomas, sorry.
Yeah, no problem. Florian, are you there? Oh. No, he's not.
Yes, I'm
Oh,
here. Sorry.
hello, hello, Florian.
Hi.
My question is, you mentioned QRAT. So in the SAT solving theory, RAT is something that incorporates redundant clauses such as block clauses. I'm wondering how a thing such a block clause can occur in QBF, because I could imagine that it could destroy some logical consistency. I don't know. I don't have any idea about block clauses thing in QBF. Redundant clauses in general.
Yes, there is a generalization of block clauses in QBF. And like for propositional logic, when you remove or add blocked clauses, you don't get an equivalent formula, but only a formula which is satisfiability equivalent. So it changes the set of models of the formula.
I see. Yeah. That's the same thing in SAT. In other higher level redundancy set block clauses, this is under development, I assume.
Yes, so there is a general
system or SPR or something like that.
Propagation redundancy hasn't been addressed, I think.
Okay. But
there is, of course, RAT. We have a generalization of RAT clauses, which is the QRAT clauses. Mm-hmm. This is what we currently have.
Okay, thanks.
Okay, so Martina, if you're ready to go, then I think it is time for us to restart the seminar. So we're switching the speaker from Florian Lonsing to Martina Seidl. The topic is still the same, QBF solving. So please.
Thank you, Jakob. So Florian has told us about the way QBFs can be solved with CDCL-based approaches, which come from the SAT world. These techniques we find there. This was already clear in the early days that the SAT technology should be generalized in order also to be applied for QBF. Also in the early days of QBF solving, it was evident, or people saw that there are also different ways of how to solve QBF, and this comes quite naturally from the semantics. So here I have the introduction slide on the semantics of models and countermodels Florian has already showed us. And if we have, for example, a QBF which starts with a universal quantifier, then we have to solve the formula which we obtain when we replace this universal formula, this universal variable by true, and we also have to replace this universal variable by false, and conjunctively combine this event. And the idea behind expansion is simply to put this conjunctively this conjunctive combination into the formula directly, and this would then lead at some point to a propositional formula, which then could be handled by a Sat solver. And this I would like to explain in the rest of this tutorial how this can be done, because there are a lot of technical things that have to be taken care of in order to make this work. And there are, as Florian already pointed out, very important optimization techniques based on the Seeger idea necessary in order to avoid the exponential space blow up that would come naturally with this expansion. Yeah, but let's have a look at the high level idea. So in expansion based solving, the idea is successively eliminate one kind of variables from a given PCNF, or in general it can be an arbitrary structured formula, so it's not necessary that we have a PCNF, and we do not rely on the clauses here. And yeah, in each of this step, this is the most naive approach to proceed with quantifier elimination. The formula is rewritten, and one variable is somehow eliminated. If it's a universal variable, then we have to introduce a conjunction of the formula of an existential variable. We can do it with a disjunction. And yeah, if there are quantifiers inside, we duplicate quantifiers, and with this we have to be a bit careful. And at some point, we hopefully have a formula that contains only one kind of variable. So we have either an purely existentially quantified variable or a universally quantified, purely universally quantified formula. And if it's existentially quantified, then we can just directly use a Sat solver. If it's universally quantified, then we have to negate the formula and can also use a Sat solver and see if the formula is valid. Problem is, as I already mentioned, in the worst case, we have an exponential blow up. If we have n variables of one kind, then the size, so we have to the power of n duplicates of the formula in the worst case, and this is what is important to be avoided. Okay, but before we look at concrete techniques to avoid this blow up, let's have a look at how we can do expansion actually. And in the approach Florian showed us, the variables were always processed from the left to the right in order to consider the dependencies. In the case of expansion, it's actually a good idea to start innermost and expand the innermost variables first, because in expansion, this avoids to duplicate quantifiers. Yeah, and when we have an expansion, then the outermost variables are anyways shared, and we do not have to introduce new variables if we start with the rightmost variable. And here I have an example where the innermost variable is an exists_y, so an existentially quantified variable. And in one step, we do this expansion and eliminate y. And we have here the subformula which we obtain when we replace y by bottom, when we set it to false. And then here we have on the right, we have the subformula which we obtain when we replace y by top. Yeah, and the formula we obtain when we expand this existential variable is not in CNF anymore, but this we have then somehow to convert back. This is something we have to take care of. Maybe this we can do with distributivity, or maybe with Seidl transformation. But here we have to be really careful not to undo our hard work in eliminating an existential variable. It's with this we have to be a bit careful. And so this is not necessarily the best idea to do. But assume we have now the formula in PCNF, then when we have innermost the universal variable, we can easily or immediately remove it by universal reduction, or we could also expand it and then eliminate it. And here in this example, this elimination then results in a formula which is already very trivial to solve. This would be a very naive approach in doing variable expansion. And we have this problem with this disjunction destroying the normal form. And this problem we do not have when we consider universally quantified variables, because then we have to conjunctively combine this formula. And therefore, an idea is not to eliminate and expand the innermost existential variable, but to have a look at the universal variable, which is second innermost in this example. And what we have to do then is, we duplicate this quantifier here. And this is in principle no problem. We then have to rename one copy of the newly introduced variable in order to distinguish the two variables, and then can obtain an expanded formula in CNF, where we just have introduced new existential variables. And this is basically the idea behind expansion. And if we would start from the left, we would have to be much more careful with the renaming of the variables. But we will see that this is then also an important property considered in modern expansion-based solving, and also in expansion-based proof systems, which characterize expansion-based reasoning. Okay, so this is a general idea, and some first examples how expansion works on a very high level. So this is not now something that's directly incorporated into a solver. And before I come to modern expansion-based solving technology, I would like to point out two very old approaches so one is the Kubos approach, which was presented in 2002, which already followed the idea to iteratively eliminate one kind of variable by expansion. It was heuristically decided which variable kind is better to eliminate, and then use a SAT solver. Kubos did not require the formula in CNF, so there wasn't this restriction on the formula structure, which made also the reasoning a bit more easier, and which also allowed a completely dual handling of the universal and the existential case. So Kubos exactly followed this idea. It eliminated one kind of variable, introduced fresh variables for those that had to be duplicated, and then at some point, and after hopefully a lot of optimizations which could shrink the formula, a SAT solver was used to decide that the formula, the value of the propositional formula. And yeah, in the end, there was only one Sat solver call. Yeah, and this was the basic idea behind the QBOS approach, and which was back then one quite well working solver. 2 years later, Bire came up with the resolve and expand approach, and he he made exactly this observation we also did before in the example, that the expansion of the innermost universal variables does not destroy the CNF structure, and yeah, the price is that we have to duplicate the existential variables behind it. And in the Quanto approach, not only universal expansion was used to solve the formula. This was the technique to deal with the universal variables, but the other technique that plays an important role in this approach is the resolve, comes from the resolve approach. And in order to deal with the innermost existential variable, simply Davis-Butman decision procedure was used, and the existential variables were eliminated by this by a DP approach as it is known from SAT. Yeah, and by this CNF structure is preserved, and also then a SAT solver is used to decide the formula at the end. And I think years later, Florian did a generalization in his master thesis where he again relaxed the requirement on a CNF structure and implemented the solver on InnoFX. Okay, these were the origins of expansion-based QBF solving, and this has two branches that it triggers later on. On the one thing, this Quanto approach became then the basis for pre-processing, which turned later out to be extremely powerful in the context of QBF. Yeah, Quanto is, for example, in the preprocessor blogger, run not until completion, until the formula is solved, but until a certain limit. And this helps to identify certain information that is lost through the normal form transformation. And when a certain amount of expansion steps and this variable elimination steps is performed, and then the formula that is obtained by doing these techniques can be much easier solved in many cases. And nowadays, most solving techniques rely on this kind of pre-processing techniques in order to find solutions fast. Yeah, this was one stream or one branch of expansion-based solving, which is nowadays still found. And the other thing is based on Seidl, which has the idea, or which is based on the observation that expansion is extremely powerful if the solver doesn't run out of memory. And in fact, it's often enough not to do the full expansion, but only a partial expansion of the formula. So not all branches have to be considered when there are multiple variables, but it's enough to consider a certain amount of expansions. And for true QBF, a partial existential expansion may be enough, and for false QBF, the partial universal expansion may be enough. And here the main insight is that we could have two SAT solvers which somehow cooperate in order to solve a formula. One takes care of the existential expansion, one takes care of the universal expansion, and they exchange information in order to do the refinement. Yeah, and this is what we have here on this schematic picture. So first we start with a partial universal expansion. So we do not expand all variables fully, but only a part of the formula. If the formula is answered, then we can stop, because then the QBF is false. If the formula is satisfiable, we use the model we obtain from the partial expansion in order to refine the formula which gives us the existential expansion. And here we have to do a validity check. If the formula is valid, then we can conclude that the QBF is true. Otherwise, we use the information obtained from solving the existential expansion, which gives us counter models for the original formula in order to refine the universal expansion. And this we do until at some point we find a solution. And the goal is to find such a partial expansion quickly in order to avoid the exponential blow-up, in order to avoid that we have to do the full expansion. And yeah, I first would like to show you the approach for two QBFs. A 2QBF is a QBF with a restricted quantifier prefix. So we have only two quantifier blocks. The first one is universally quantified. So we have the universal variables u, and the second block contains existential variables e, and then we have the propositional matrix, which is quantifier free. Okay, and having just a 2QBF makes the situation much easier, and later on I would like to show you an approach which allows to generalize the idea to arbitrary QBFs, so where we have no restriction on the number of quantifier attenuations. Okay, so this expansion-based solving approach first starts with guessing an assignment of the universal variables. And if we're lucky and we plug this assignment into the formula, then the propositional formula which we obtain is false or is unsatisfiable. So we have only the existential variables there, and then we are done. Yeah, so we start with the formula phi, with the matrix phi under the assignment alpha, and if the formula is unsatisfiable, then we can conclude that the formula is false. Otherwise, we get an assignment tau to the existential variables, and we use this assignment tau now for setting the values of the existential variables, and this we use for refining the existential abstraction, and here we have to solve a validity problem. Therefore, we do not put an or here. Yeah? So we have the first part of the formula, the refinement we obtained before. In principle, we would start with bottom, but we negate it, so we start with top, and then we have the negated or and the negated formula in order to check the validity. Yeah, and if the formula, if this existential expansion we have obtained is unsatisfiable, then we can conclude that the formula is that the original QBF is true. Otherwise, we get we get an assignment to the universal variables, which we then use in the next round in order to check if the formula under this assignment is satisfiable or unsatisfiable, and we proceed like in the first iteration. And the nice thing is, when we have a 2 QBF, we do not have to take care about the duplication of the existential quantifier, because all variables which we have here are then renamed in some sense anyways in each round, and therefore it's enough to consider only one instantiation of the propositional formula. Yeah? And yeah, this gives us already a very nice algorithm for solving 2 QBFs, where we have 2 subsolvers cooperating in order to solve a formula. So one produces candidates for models, propositional models. One produces candidates which are propositional counter models, and these assemble then to the overall QBF model. And this approach was then later on by Mikuláš Janota generalized to arbitrary prefixed QBF by using a recursive application of this approach, so where the formula is processed quantifier blockwise, and it is implemented in the solver RAREX, which is now, I think, almost I think it's 8 years old or so, and it's still a very good and efficient solver, although a lot of things have happened there. And this was really an idea which showed that in QBF there are alternative ways of how a formula can be solved, and that CDCL is not the only way to go in order to be efficient with space. Yeah? And what I would like to quickly sketch is a more recent approach, which takes up the idea, which uses a non-recursive Seeger-based approach. So it does not use this approach which we have seen before in a recursive manner, but it uses the idea of directly annotating the variables such that we can build the expansions and instantiations of the formula. And here the basic idea is that we have 2 sets of assignments. So we collect the assignments of the variables, and one set contains the universal variables, the other set contains the set of existential variables. The set for the assignments of existential variables is called S. The set of assignments for the universal variables is called A. And we use these sets for building the abstractions, so these partial expansions. And these sets give us the parts of the expanded formulas. Yeah, and we have to start somewhere, so we initialize A, for example, with some arbitrary universal assignment, but in fact, it could also be started with S, doesn't matter. And then we proceed with a loop as before, and we will see that the pseudocode of this approach is very small. It's almost like for the 2 QBF. We check the partial expansion and check if it's answered, then the QBF is false. And otherwise, we update the set S with a new assignment which we obtain for the existential variables, then we use this assignment for refining the existential expansion, check if the formula is valid, and if yes, the QBF is true. Otherwise, we update the set of assignment A. And what I didn't tell you yet is how we deal with the quantifier dependencies and how we deal with the renaming. And here, the core concept is to introduce universal or existential annotations. On this slide, I have the universal annotations. And when we think back about this assignment tree we have seen before, then for each quantifier which we somewhere reach in the tree, we know exactly the path how we go there, how we got there. And this gives us exactly a unique annotation for the variable, and this gives us a unique variable name. Yeah, so assume now we have universal variables x and existential variables y. What we do is we first define a total order also for the universal variables with respect to the prefix, because we have to use sequences of universal variables for the annotation, and we have to do this always in the same order. And yeah, we have an assignment which maps the universal variables to some true value. And then we obtain the universal annotation of a formula by simply assigning the universal variables according to the assignment sigma we have seen before. And for the existential variables, we introduce fresh variables which are now annotated by the assignment of the universal variables. And for this, so we get a string of top and bottom, and this is exactly reflects the assignment of the universal variables. And with this, we have a very unique, so we have a unique identifier for each duplicated variable, and we can use this for doing the expansion. Yeah, here I have an example. We have the formula for all A exists X, for all B exists Y, and the assignment where A is set to top and B is set to bottom. And if we have this clause here, then not A and B, the two literals go away. X is annotated with top, because the only preceding universal variable is A, and A is set to top, and Y is annotated with top and bottom, because the two preceding universal variables are A and B, and they are then set according to this assignment. And existential annotation works accordingly. And this is everything that we need in order to have now an expansion-based algorithm for arbitrary variables. And here we have now the set A of universal assignments and the set S of existential assignments. We pick an arbitrary universal assignment in the beginning, then build the abstraction according to this formula. If the formula is answered, then we return false. Otherwise, we get a new assignment to the existential variables, put it into the set S, and then use the set S to build the other abstraction, check it for validity. If it's valid, then we're done. Otherwise, we refine the set A and so on. And it can be shown that in each iteration, set S and A grow, and at some point we have decided the formula. Yeah, and this is basically a non-recursive approach of solving a QBF with this Siga-based approach, and it's I think it's quite natural implementation of the semantics of QBFs. Here I have an example which I would like to show you very quickly due to the proceeding time. I will go very fast over it. So here we have a QBF which is in not in CNF because it was more compact to write it down this way. So here it doesn't matter. And we start with some assignment of the universal variables, which are A and B. So both A and B are set to false. Then we get the annotated formula where we have only the existential variables that are now annotated with the values of A and B respectively. And this is now a purely propositional formula. And we solve this formula, and this gives us now an assignment to X and Y. And this also gives us now a new partial expansion now on the variable A and B. For example, when the stat solver returned us top and bottom returned us when the stat solver returned us top and bottom for the formula we have here, we then get not A and not B top. Here it's important that A is the outermost universal variable, therefore it has no preceding existential variable, and therefore it has no annotation, and B has only the X as the annotation. Yeah, and with this we can proceed, get new assignments which we use to refine the formula on both sides, and at some point we reach the situation that we cannot build up a model, a QBF model here. We have a counterexample, and we cannot further refine the formula, and therefore we can conclude that the QBF is false. Yeah, this is a very quick and short example. Yeah, and this is also very closely related to the proof system for all expansion resolution, which Florian already mentioned. And yeah, I would like to quickly also introduce this proof system and also show you how it relates to an idea I just presented. In the for all express proof system, we have two rules. And the first rule is the expansion rule. And the expansion rule exactly does the same thing as the annotation of the variables as I have shown you before. So it takes a clause C. Yeah, this is a proof system which now works on clauses. It takes a clause C from the QBF, and yeah, what is important is that the assignment that is considered for the universal variables does not have to make the clause C true. So it's important that it's not a satisfying assignment of C with respect to the universal. So that this universal assignment is not satisfying C. And with this, we then get the annotations of the existential literals in the clause, and the universal literals yeah, are simply set to false and then eliminated. So we have one rule for annotating literals and getting pure propositional clauses, and the second rule we have is propositional resolution. Nothing special about this. We now have these annotated variables, and yeah, these are unique identifiers, and we just resolve over these annotated variables. And yeah, here I have an example. So in the first phase, we do this annotation. So for example, let's take the first clause where we have X or A or Y. A is universally quantified. We have to, we may only assign it with or we may only use an annotation where A is false. So we get the clause X or Y and annotate it with not A. Here I have now written down the literals because it wasn't necessary to save the space. Yeah, here I have not written down the truth values, but the literal names, which is maybe also easier to read. Yeah, and this we can do for all clauses, and then we simply can do a resolution proof, derive a contradiction, and decide that the QBF is false. This is the basic idea behind the for all express proof system. This proof, so if we have this expansion-based approach I just presented, we have a solver where we can create such proofs for false formulas. And if we have these proof, there have also been strategy extraction approaches being presented, which yeah, I will not go into details here. It's about assigning values to the existential variables, then rewriting the proof in a certain way, and then there is only one kind of annotation for the outermost universal variables, and this gives the values for the outermost variables, and then this can be repeated until all values are decided for the universal variables based on the assignment of the preceding existential variables. Yeah, here I would have an example, but due to the preceding time, I will skip this. And yeah, I just would like to show you now the full picture of the proof complexity landscape of the proof systems based on resolution, on Q resolution, and on expansion. There are also generalizations of this for all express proof system where the annotations do not have to be decided in the first phase, but where they can be done later during the proof. So there is an instantiation rule, and even more general is when in this calc proof system, annotations can also be merged according to certain rules, and this gives a lot of power and gives also a very interesting landscape in the proof complexity field for quantified Boolean formulas. Yeah, and with this, I come to the conclusion of this tutorial. Yeah, in QBF, there are a lot of opportunities for new approaches, both in theory and in practice. And over the last year, we have seen much progress, much innovation, and I'm pretty sure there's much more to come, and that there are many more ideas which have to be followed. There are also a lot of challenges. One challenge concerns the tooling. So we need robust and integrated workflows and tool chains where all comes in one. At the moment, it's a bit distributed. We do not have the standards as in SAT yet because there are still many questions open from the theory side. And yeah, we have to work more in order to get a uniform picture. And yeah, it would be very nice if we would have a universal certification framework as we would have it as we have it in SAT, in order to check the results, and also in order to extract Skolem and Hepro functions. Yeah, there are a lot of topics that were not covered in this talk: full proof complexity, non-QBF solving, preprocessing. On preprocessing, I will give a talk on next week, Wednesday's workshop. Then there are even more very, very powerful techniques in practice based on clausal abstraction. Yeah, there is much more theory on symmetries, dependency QBFs, and so on. So there is a lot of stuff ongoing which could be talked about. As a pointer and advertisement, I would like to point out that there is a new chapter co-authored by Florian, Olaf Beiersdorf, Mikolaš Janota, and myself in the new edition of the Handbook of Satisfiability, and a lot of things discussed today and much more is covered in this handbook article. Yeah, and with this, I would like to conclude and happy to take questions. Thank you.
Thank you, Martina. Thank you, Florian. I'll be applauding on behalf of all attendees of this seminar. So we certainly do have time for questions.
Yeah, I have a really mean one, because I would really like to know the answer. What will be the killer application for QBF?
So my feeling is that synthesis has a lot of potential, and this was also a very strong driver in the last years. And yeah, I would bet on synthesis.
Can you say something about how different techniques compare? I mean, also, what would to the extent that the question makes sense, what would a typical formula look like? I mean, is there deep levels of nesting of quantifiers, or just a few levels, and are different techniques of solving helpful for, say, shallow or deep formulas, those kind of questions?
Yes, I mean, this is also not entirely clear, but Florian has done a quite extensive study on this topic. And it turns out that this approach, which I just presented, is very good on deep quantifier nestings. The recursive approach prefers less quantifier alternations. But in general, it's good to reduce the prefix and have a few quantifier alternations. And yeah, but what one can say is that this technique, which I showed, works pretty well on many quantifier alternations. So this is beneficial for this approach.
So I have a quick question about kind of related to that quantifier alternation you just mentioned. So you introduced the cigar-based algorithm, also the non-recursive one, and you mentioned that there's a generalization of that. Does that mean using that approach we can deal with different form of the alternation? Because in the example we see for all exist, it can be by using that expansion, but if it is in other form, can we still do that?
I'm not sure about the question, but what do you mean with other form?
Like if we have starting from exist and then we do the expansion.
It's completely independent of the quantifier structure. This can be done for arbitrary quantifiers. And I just started with the 2QBF approach because, in fact, this approach it's very simple, but writing it up concisely is very technical, and this you don't have with the 2QBF approach, because there you have less dependencies to be considered, and it's easier to write up. But in general, both the recursive approach and the non-recursive approach can be applied to arbitrary prefix structures.
Would that affect complexity a lot?
To what?
Complexity. I was thinking about for different complexity, like if we want to calculate all those expansion. Yes.
So you mean from runtimes or from theory?
From theory.
yeah, I mean there is definitely some connection, but I don't have any details on that.
Okay, thank you.
I actually have one question. I'm curious, what do you think? How could we use some of these techniques within SAT? As you know, there's been quite a lot of interesting work that lately has been put into effectively borrowing ideas from other areas. For example, local search solving and sort of shoving it into CDCL solvers, and also combining, for example, a look-ahead search with CDCL search. And so there's been, and I mean, I personally am, of course, have been working on some of this, and I know that also others have been working on some pseudo-Boolean. So there are some interesting work that effectively tries to combine ideas from other areas and shoving it back into SAT and see, because of course you have also, or your area seems to have been partially at least informed and perhaps also inspired by some of the work that has been done, on SAT. And I think this could be sort of like this virtual cycle where, some of the work that is inspired or informed by the work from the SAT community, and then some of this can be sort of cycled back, and the work that you have done, can be used within the SAT community. So what are your ideas, and what do you think would be like interesting avenues to sort of take ideas from here and shove it back into SAT?
Yeah, one thing I could think of is that there are maybe some pre-processing techniques which are beyond NP, and which would help to get information out of the propositional formula that could maybe help the SAT solver to find a solution faster. So if there is a certain part of a problem extracted, and then maybe some expensive QBF expressible pre-processing technique maybe is used, and this could then maybe help to guide the SAT solver for the search. I could imagine. As also to use QBF maybe as a preprocessor for some, or in processor for some expensive techniques. This would one thing that comes to my mind.
Yeah, pre-processing is effectively what has been happening. So, for example, the local search solvers have been used as effectively top-level processors. You can call them pre-processors, in-processors, whatever you like. But actually, interestingly, the latest, the one that won second place last year, was doing it in the middle of the search, at the middle of the search tree, which was very strange to me. But I know that Armin and myself both use, so the first and third place both use top-level local search solvers as effectively pre-processors or in-processors to inform the search. In this case, the parity, the default parity of the variable. But okay, that's interesting. Yeah, thank you.
Are there further questions? Otherwise, I just want to take the opportunity also to mention that all registered workshop participants should be able to log in GatherTown at the Simons Institute workshop space. So I put the link in the chat now again. This might also be a further opportunity to continue the discussions. And if there are any questions, now is a good time to ask, but I don't see anything in the chat, I think. So I think that we'll just thank Martina and Florian again. Thank you so much for a wonderful seminar, and for those of us who can make it, the Simons workshop GatherTown space is waiting. Thank you so much.